Hi everyone and welcome to today's webinar, Unpacking the Digital Technologies Curriculum. If you'd like to ask a question throughout the webinar, you can do so just by clicking on the speech bubble with the question mark inside, and I'll be here supporting the presenter in the background, answering any questions that you may have throughout, and then we'll also have a few minutes to ask questions at the end directly to the presenter. If you'd like to earn a certificate for today's webinar to go towards your PD hours, you can do so just by logging on to training.smarttech.com and then clicking on the Mark Complete button at the end, and that will automatically download you a PDF certificate. I usually have the webinars up and running with the certificates connected at the end the following week, so next Monday, Tuesday, they'll be up ready to go. If you have any troubles with that, you can send me an email. I'll put my email in the chat box. Okay, now I'd like to introduce today's presenter. We have Associate Professor James Curran. James is the Academic Director of the Australian Computing Academy. He is the Associate Professor in the School of Computer Science at the University of Sydney. He's a Director of the National Computer Science School, the largest computer science school outreach program in Australia, where last year over 17,000 students and teachers participated in the 5-week NCSS Challenge. He is the co-founder of Proc Learning, an edtech startup that aims to teach children everywhere to code. He is the writer of the Australian Curriculum, Digital Technologies, the new National Computing Curriculum. And in 2014, James was named ICT Leader of the Year by the ICT Educators of New South Wales and the Australian Council of Computers in Education. So without further ado, I would like to hand it over to James. Thanks, James.
Thanks very much. All right, I'll just switch over. There we go. Okay, good. Hi, everyone. Thanks for the introduction. I'm going to get stuck straight in. So I was one of the authors of the Australian Curriculum, Digital Technologies. And I want to talk a little bit about, over the next 25 minutes or so, some things that we discussed in the writing team when we were developing the curriculum that don't necessarily appear or so clear in the curriculum documents, but really help teachers a lot in terms of how the curriculum can be delivered in the classroom and so on. So I started here with 2 photos. My son Thomas, who's now 7 years old and goes to Darlington Public School in Sydney. He was born 2 weeks before the curriculum started. So here he is in July 2012, and then last month in Sydney. So he's 7 years old, which means that the Digital Technologies curriculum is also already 7 years old. In fact, it's really 9 years old because we started with a shaping paper in 2010. We began writing in July 2012. The curriculum was endorsed by education ministers on the 18th of September 2015. In New South Wales, we've been a bit slow to actually implement the curriculum, so we only started it in K to 6 and 7 and 8 February this year. And if you think about that, the students that are in kindergarten this year will be the first full product of this new curriculum, and they won't leave the school system until 2031. And then they're likely to have 3, maybe 4 years of further education before they actually pop out of the other end of the education system entirely. And if you think about that, that's, we're talking more than a quarter of a century between when the curriculum was first designed to when the first full product is going to pop out the other end. Now, luckily, not much has changed in terms of technology in the last 25 years. In fact, the collection of things here, many of them were the last 15 years or so, and 25 years actually takes you back to the beginning of the retail internet in Australia. So a huge amount of change from a technology and society perspective has occurred over that time. And a big thing that we were discussing in the curriculum writing team is how do you actually develop a curriculum in an area that moves so rapidly that can actually be robust to that change. And the decision that we came up with in the writing team was to try and focus on the key ideas, the key skills that have been true for a very long time, true long before we had digital systems, right through to whatever the technology we have today is, and will hopefully be robust to any future technology. And so we focused on 10 key concepts. Now, I'll show you in a minute where you can actually see those 10 key concepts. Mostly they appear in the preface material to the curriculum, which in my experience, not many teachers have had the time to read through, although I would strongly encourage you to do so. So those 10 key concepts are abstraction, data representation, the collection of data and its interpretation, the specification of a problem, its solution in one or more algorithms, and then the implementation of those algorithms in some form of code or other software. Digital systems is the current technology we use to execute those programs. And then the last two key concepts, interactions and impact, what I call synthetic content key concepts. So they describe things that maybe a computer scientist wouldn't necessarily recognize, whereas all of the other terms would be well known to a computer scientist. So interactions covers human-to-human interaction mediated by technology. So, for example, communication and collaboration tools, and also covers human-computer interaction. So building systems so that they most naturally can be used by humans. And finally, impact covers all of the ways that digital technologies has remade and continues to remake every aspect of our society, and both the positive benefits and the unintended negative consequences of that. Now, as I said, these 10 key concepts, many of which, like data representation and algorithms, have actually been around for a very long time. And so what we believe is that no matter what form of technology we're using 10, 20, 50 years time, these 10 deep ideas will still be core to digital technologies. If you're interested in getting a copy of these definitions and the 10 key concepts, we've actually got a poster of that you can get on the ACA website, and I'll talk about resources that the ACA has available in a bit. So how do the key concepts get split by strand? Well, in the knowledge and understanding strand, we have digital systems and data representation, and then many elements of the processes and production skills corresponds to some of these key concepts. So for example, investigating and defining in the production sequence corresponds to specification. In digital technologies, the thing you're designing is an algorithm. And then of course, the producing and implementing is actually the implementation of that code. And then finally, under evaluating, collaborating and managing, we have interaction and impact. And for New South Wales teachers, I've just put in the speech bubble here at the top that we have a slightly different terminology in New South Wales for those production stages, but they correspond to the same key concepts. Now, in terms of how you actually see these key concepts in the curriculum, unfortunately, if you go to ACARA's website and go to the website version of the Australian curriculum, you won't see any of those 10 key concepts described except in the preface material. But if you go and look for a 2-page PDF that is called the sequence of content, it actually has laid out all of the Australian curriculum content descriptions against each of these key concepts. So for example, here on this slide, you can see that we've got the digital systems sequence from foundation, which is kindy or the preppies, depending on where you are in the country, right through to year 9 and 10. And in a minute, we're actually going to unpack one of those particular key concepts. But the thing that I want to point out here, if you haven't already seen this, is this 2-page PDF, and here's the second page, is a really good way to interrogate the curriculum, because every teacher needs to know what's the input, so the band before the one I'm teaching, what am I currently teaching, and what will students be expected to do in the band after mine, and this PDF really helps with that a lot. Now, if you're in New South Wales or WA, or to a lesser extent Victoria, where the curriculum is different, I would still strongly recommend that you go and look at this 2-page PDF, because this sequence is actually a lot easier to follow in this form than it is in your respective state versions of the digital technologies curriculum. And in terms of where to find it, Unfortunately, every time ACARA redoes the Australian Curriculum website, it gets a bit harder to find things than the time before. You have to click on Understand How Technology Works, and then under PDF documents, you'll see the digital technologies sequence of content. Click on the Read More, and then you can download that PDF. As I said before, the Australian Computing Academy, one of the many hats that I'm involved in, produces a number of resources to support teachers in the development of delivery of the digital technologies curriculum. And you'll see in the middle of this slide here the key concepts poster. It has classroom-friendly definitions of each of those 10 key concepts, and there's a PDF there that you can download. I'll also point out while I'm here, there's a set of cards that allow you to distinguish between digital technologies and the ICT capability. They're great for teachers to use to discuss with each other where their school is at in terms of digital technologies implementation, and also understanding the distinction between DT and ICT. And there's that poster. We also develop a number of other resources. So we have collections of unplugged resources and activities to support the curriculum. And we also have a number of challenges that are online challenges that support automated marking for the digital technologies, mainly the implementation, so the coding from year 3 through to year 8. So we have visual programming in Blockly, we have Python programming as well, and in many cases we have the same content both in Blockly and in Python. So if, for example, you're a year 7 teacher and you've got quite variable inputs from your feeder primary schools, maybe some of your students would do a Blockly version of activity and your stronger students would do the corresponding Python version. Now, the process of writing a curriculum is both an absolute privilege, but also quite a frustrating process, because our job was to pack all of our understanding about the curriculum into a very small number of dot points for each of the bands. And your job over the next decade is to wonder what the hell we were thinking when we were writing that. And just to give you an idea of how few words we're talking about, in Foundation to Year 2, it's literally 6 dot points with 94 words and an achievement standard of only 74 words. By Year 9 and 10, we get to the relatively luxurious 9 dot points, or content descriptions, and 9 sentences, 157 words. So, of course, it's not surprising if you find yourself reading the digital technologies curriculum and going, I have no idea what they actually meant by that, or how that might look in the classroom. Don't be surprised. That's kind of the way we have felt in the writing process as well. And because of that, we've been developing a resource that we call Unpacking the Curriculum. So again, if you go to the ACA website and either click on Unpack the Curriculum at the top, or you can see the URL down the bottom of this slide. So what we decided to do in Unpack the Curriculum is expand on each of these content descriptions with both a definition of the various elements of each of the content descriptions, but then also, I think the most valuable thing is an explanation of what we expect that might actually look like in the classroom. So the most frustrating thing with writing the curriculum is that there was no opportunity to explain to teachers how we thought this should look. And of course, when we were writing the content, that was the most important thing. If we couldn't describe to each other how this would look in the classroom, then it never made it into the curriculum. So here you can see we've got each of the key concepts aligned with the content descriptions for each band, and then we've aligned by highlighting both the band description and the achievement standards against each of those content descriptions. So that helps you go from the really compact rolled up version of the achievement standard to expand out into each of the content descriptions. And then for each of the content descriptions, we break it up. So for example, for digital systems, in this band here, we've broken it up into systems, network, and security. But in the Year 3-4 band, which is what this content description is, there's no security as part of it, but there is identify digital systems and explore digital systems with a purpose, and here transmit data. So for example, what we expect students to be able to do in year 3-4 in terms of transmit data is students understand that different types of data can be transferred between digital systems, e.g. streaming music from an online service or using a smartphone to call a friend. That gives a much clearer definition or expectation of what you would need to do and what your students would need to be able to do to satisfy that part of the content description. And here's another one for the same band in terms of algorithms. So what does it mean to follow a sequence of steps and decisions needed to solve a problem? Well, if you look under follow algorithms, you can see exactly what we would expect students to be able to do. Follow rules to form progressive verbs, such as eat converted to eating, run to running, make to making, and know what step they're up to. So can the students follow a sequence of steps without actually getting lost in where they are in that sequence? And it's on that point now that I'm going to switch to talking about one of these key concepts. Now, today's webinar is quite short, only 25 minutes, so we're not going to be able to get that far into this. But this is actually what we spend a lot of time doing when we run in the Australian Computing Academy our 2-day professional development workshops. So consider this to be a bit of a taster. If you like what we're discussing here, then I encourage you to join our ACA mailing list. So again, if you go to aca.edu.au and scroll to the end of the page there, you'll see contact us or join our mailing list. And then we can tell you when our next workshop is going to be near you. So let's look at the definition of an algorithm. An algorithm is the precise description of the steps and decisions needed to solve a problem. Anyone who has followed or given instructions, navigated using directions, followed a recipe, all kinds of things, has used an algorithm. So I'm going to give you an example of this now. And the example is, what are the sequence of steps that you need to make a Vegemite sandwich? Now, normally what I do is actually ask people to sit down and write down the steps or discuss it with someone else. But here, since we're in a webinar, I'm just going to run through them very quickly. You might take 2 slices of bread, apply margarine to both, put Vegemite on one, then close the sandwich. Now, notice when I did that particular description, it basically assumes you already know what a Vegemite sandwich is. Imagine that I had to explain to an alien or someone who didn't know what a Vegemite sandwich was how to actually make one. That set of steps that I just followed or just described is way too abbreviated for someone that really doesn't know what it is that they're making. And also, even within those steps, there are many opportunities to get those steps wrong. I'm now just going to switch over quickly to show you an example. Oops, I've already got it open. Of someone doing exactly this. So this is American, so it's a peanut butter and jelly sandwich instead. But you'll see a dad here following the exact instructions that his kids are giving him for making a peanut butter and jelly sandwich. Let's see how this one goes.
Get 2 pieces of bread. Get some peanut butter. Get some jelly. Open the peanut butter. Get a butter knife. Put the butter knife in the peanut butter.
Look at that face.
Take the butter knife out of the peanut butter.
You did it wrong. No.
Take 1 piece of bread and take the butter knife that has the peanut butter on it and spread it all over the top of the piece of bread.
Dad,
That's the top.
I mean the sides.
Squirt some on another piece of bread. Take the butter knife, rub it all over the top of the piece of bread.
I quit. You're not making any sense. Sorry, you ruined it on purpose. He knows how to make one. I know it.
So we won't go through the whole thing, but it's 7 and a bit minutes of pure joy. I strongly recommend you go and watch the whole thing. The key thing here is that the dad is following exactly the set of instructions that that his kids have described, but doing so in the most perverse manner possible. And this is a very effective way for kids to see how difficult it is to actually define the sequence of steps needed to solve a particular problem. So when we talk about our Vegemite sandwich example, my strong recommendation is you actually bring all of the ingredients into class, get kids to write down the steps, and then find ways to actually deliberately misinterpret their instructions, and then ask them to rewrite their instructions again to see whether they can actually stop you following it in a strange order. And so you can see within that, we're already starting to get some of these key ideas of an algorithm. How do you actually describe something so that anyone could actually solve it? And how do you follow those steps precisely to achieve the desired outcome? Other questions you could ask about is, what order must the steps be done in? I mean, is it acceptable to put Vegemite on before the margarine? The short answer most people would say is no, but actually it produces exactly the same result. What if you were making a lot of sandwiches? So I had one Vegemite sandwich pretty much for every lunch for my 13 years of school. I had 3 younger siblings. We all had Vegemite sandwiches. So every Sunday night, my mum would make 20 Vegemite sandwiches. Now, of course, she could do that by making the sandwiches one at a time, but she didn't. She developed a more sophisticated algorithm for solving the general problem. And that more sophisticated algorithm involved laying out 40 slices of bread, putting margarine on half, margarine on all of them, Vegemite on half, closing, slice, Glad wrap into the freezer. Now, my mum's no computer scientist, but she succeeded in finding a more intelligent, more efficient way, a more efficient algorithm to solve a particular problem. And here is one of the key things that I'd like you to get out of this webinar, is that digital technologies isn't just about turning every Australian child into a developer. There are many things kids can learn in digital technologies that will apply in every aspect of their life, no matter what it is that they choose to do with their future. I'm going to go for another example. So I'm thinking of a number game. In this game, you basically need to guess a number. So I might say, I've got a number in my head between 1 and 100, and then you're going to guess a number, and I'm going to say higher or lower with that number. And we're going to keep going until you succeed in getting my guess. Now, getting my original number in my head. Now, the best way to play this algorithm is, again, something that most people are able to work out for themselves, which is to start by guessing 50, because then you eliminate half of the search space immediately, and the answer must be in the other half. And so you keep repeating that process over and over again. And I've got a little example of that here with a phone book. Most people have worked out how to actually use a phone book, although obviously modern kids now would go, what is that thing? Most people are able to work out how to search a phone book effectively by starting in the middle and then going, is the name I'm looking for in the left half or the right half, and continuing to search, and then break the halves up again. Now, in this webinar, we're not going to have time to really go through how powerful this algorithm is. But just to let you know, if I had a phone book that consisted of 1,024 names, this algorithm would only require 10 steps to find the correct answer, which is pretty amazing. And if I applied that to the whole population of the world, let's say 8 billion people, it would only take 33 steps to find any human on the planet using this algorithm. Now, the algorithm, as it turns out, even though nearly everyone who uses a phone book is able to work it out, is a very famous algorithm called binary search in computer science, and it's extremely powerful for searching through sorted information. So let's finish by tying this back to the curriculum. So if you're teaching in Foundation to Year 2, students are expected to follow, describe, and represent a sequence of steps and decisions, algorithms, needed to solve simple problems. By Year 3-4, we add that students should be starting to define their own simple problems. Now, these could be problems they're already familiar with, but then they're still following a sequence of steps and decisions needed to solve those problems. That Vegemite sandwich example already has those elements within it. By Year 5-6, students are expected to design, modify, and follow simple algorithms. So the key addition there is that they need to be able to take an existing algorithm and change it in some way. And then we're going to add, in addition to sequence of steps and branching is just a more formal way of describing making a decision. The final addition is iteration. So an algorithm that actually involves repeated steps. An example of that might be keep washing your hands or keep rubbing your hands together until the soap is off when you're washing your hands. And so that would involve an iterative process of checking, are my hands clean yet? No, keep rubbing and repeating that potentially several times. In year 7 and 8, students are expected to design algorithms represented diagrammatically. So that could be a flow chart or a decision tree, and in English. And so that's basically writing just like we saw before, the English description of the peanut butter and jelly sandwich, and trace algorithms, which means follow an algorithm very carefully to predict its output for a given input. And I'll leave the year 9 and 10 one off for this time round. So I want to just conclude by making it clear that algorithms are absolutely everywhere. We follow, create, and modify algorithms every single day. Grammar rules, recipes, instructions, directions. As a teacher, you are constantly getting your kids, both in the classroom and in the things they're learning, to use algorithms. You teach algorithms every single day. Spelling rules, how to add two two-digit numbers together. They're all examples of an algorithm. The other thing that's really the key thing for kids to understand about algorithms is they're actually really hard to define succinctly and unambiguously. And digital technologies provides every student the opportunity to understand more deeply how algorithms appear both across all learning areas and across all aspects of their life. And I just want to conclude with the underlying philosophy, I guess, from the writing team. We're less worried about any particular details of both technology, skills, and knowledge that students are learning. And we want more than anything for them to have this disposition, which is we want them to want to be the master of the digital technologies that they're using and not the slave. And if we could get them to achieve that, then that gives them the attitude that they'll continually learn as technology changes around them. And I like to leave it there. So I've got my email address down the bottom and our main helpline, help@aca.edu.au. If you want to find any of the resources, please go to our website, and I'll hand back over for any questions.
Great, thanks for that, James. I always love that YouTube video clip. It's always
Good
fun
fun,
to watch. Yeah, it's a good one. Always makes me laugh. So if anyone would like to ask any questions, they can do so. Quick wrap up. If anyone would like any free resources for their class lessons, they can go on to content.smarttech.com, and that will bring up the Smart Exchange, also known as SMEX, and there's loads of awesome content on that shared by teachers from all around the world. For those who came in late, if you'd like to earn a certificate towards your PD hours for this webinar, you can do so by logging on to the training.smarttech.com, clicking on the Mark Complete button at the end, and I usually aim to have the webinars up the following week, the latest Monday, Tuesday. So next week, Monday, Tuesday, this webinar will be up. And lucky last webinar next week, wrapping up the term, we have using SLS in a high school math setting. We have Vicky from St Cuthbert's College in New Zealand, one of our Smart Exemplar educators, presenting next week, Wednesday the 27th of November. So we'd love to see you all there. And that's it for now. Have a great afternoon, everyone. Thanks a lot. Bye.